Again, grade 12. So this is an extension of the previous video, which is notation and rules of differentiation. We're just finishing a couple of additional examples which are slightly more complicated. So we ended off in the previous video doing this particular example, and this particular example I said very, very clearly, in order to use the rules for differentiation, you cannot have a product like that, which is only one term. And you cannot go and, for instance, say, oh, let me find the derivative of x, the derivative of -3, and then find the derivative of 2x and the derivative of 1. That is not allowed. So I just want to quickly reiterate over here. If you do this, and by the way, I'm going to write this in hopefully a very icky pen, which my class will know icky is green. So I will say, if I go and I say dy over dx over here is then equal to, hey, the derivative of x is 1. Now, I have discussed this before, where I said you take the 1, which is over there, you multiply it, and you make the exponent 1 less, which is x to the power of 0. So because it's x to the power of 0, it's 1, so the answer is 1. Then if you go and you say the derivative of -3 is 0, and then you say the derivative of 2x is 2, the derivative of 1 is 0. This, people, is 100% wrong. This is so wrong. It will never ever be right. I cannot state enough how wrong this is. You cannot find derivatives if it's inside a product. You've got to first do the algebra. And then in the previous video, I said also very clearly, watch your notation. This is not dy over dx. This is still y. This is just a simplification. So I use that y to show it's still the function of y. It's only after I find the derivative, so after I've employed the differentiation rules, that I indicate, okay, now it's the derivative of y with regard to x. So please watch out, people. You cannot find a derivative if it's part of a product like this. Then also, in the next example, it's not a product. This is what we call a quotient. It's the top function in the numerator divided by the bottom function in that denominator. Now, this is exactly the same rule. You are not allowed to find the derivatives of these terms if there is a product, or in this case, a quotient going on. So I will first have to simplify this before I can employ my differentiation rules. And when I simplify this, you should notice most algebraic fractions, when I simplify, first factorize them. I've got this rule that I actually teach my grade 9s, where I say F, people. So let's write this down. F, which stands for first factorize your fractions. So please, people, remember, first factorize your fractions. This is obviously if it can be done. Now, again, watch the notation. I'm going to go equal to, and I'm going to keep this dx over there. Now, the reason I don't drop the dx is I'm not allowed to drop that until I actually find the derivative. This is a lot like the notation we discussed in the video on limits, where I said, until you calculate the limit, until you do the substitution in limits, you cannot drop the limit notation. And this notation works the same until you actually employ the rules for differentiation. So until you actually find the derivative, you can't drop this. You've got to keep on showing, I'm gonna find the derivative, but not just yet. Right, so factorizing the numerator, which is the trinomial, I go x times x, 2 times 3, and it's got to be -3 and +2. And then I've got that lovely common factor over here, and I'm going to divide that x plus 2 into that x plus 2. So now, simplified, this particular function becomes x minus 3. Again, please note, I'm still writing that dx because this is still the original function. I haven't actually found the derivative. But now it is in the format where I can find the derivative. Now it's a term minus another term. So now, because I'm finding the derivative using my differentiation rules, I can drop that dx. And I can say the derivative of x is 1. Now, I didn't mention this before, but I do actually just want to quickly talk about why I can easily see the derivative of x is equal to 1. And before I do that, also remember the derivative of a constant, so in this case the derivative of -3 is 0. I just want to quickly talk about this and say, for instance, if I write that y equal to x minus 3 out over here, this, people, is a straight line. And if you recall, straight lines are written in the format y is equal to mx plus c, where m is what? Hopefully you guys should answer that on your own. M is the gradient. Now again, people, I say derivatives, you say gradients. The derivative is the gradient. So if you look at that equation, because I know the gradient of that particular equation is 1, so the gradient is 1. Therefore, the derivative is 1. So that's how, whenever we have these linear functions, it's actually incredibly easy just to see, oh, the derivative of x is equal to 1. And I'll show that to you again up top here in the previous example. The derivative of minus 5x is just minus 5. Now obviously this is something completely different. Please don't tell me, oh, why isn't the derivative 2? That's a quadratic function. It's specifically only with these linear terms. So if I have a linear term, x to the power of 1, I can just say my derivative is negative 5. So that's a nice little shortcut where I can just go and say, oh, the derivative there of that x is equal to 1. So that's just a side note to make things a little bit easier to do. Now the next examples is not from the textbook. These ones are past paper examples. And in the next video, the entire video is just going to discuss past paper examples from either the IEB examinations or from the Department of Basic Education, which are the DBE ones. So in this particular one, you'll note, and I've said this before, they might force you to use their particular notation. So they ask you determine dy over dx, and because dy over dx means the derivative, they're asking determine the derivative of that function defined as y in terms of x. Now this one also first needs to be prepped. You will find a lot of these derivatives, the rules is not the important bit always, because the rules is actually very easy to use. It's prepping that particular equation or that particular function so that you can use the rules. Now this is something we haven't seen before. The moment I have an x in my denominator, please remember that is not allowed. So right there we have our first little problem, x squared is in the denominator, I've got to go and fix that. And then the second problem I've got over here is I've got x in a surd or a root. So I say it's the fifth root of x. So whenever I see these x's in the denominator, or whenever I see x underneath a root, I first have to prep the algebra before I can use the differentiation rules. So while I'm prepping the algebra, this is still y. I haven't been able to employ the differentiation rules, so I can't tell people what I'm writing now as the derivative. It's not. It's simplifying this or getting that into a format where I can finally find the derivative. Now to get that into a format, we have to go back, in this case, to grade 8 and grade 9 mathematics, which tells you that x squared, if it's in the denominator, I can move it into the numerator, if and only if I make the exponent negative. So if there's an x in the denominator, I always have to go and move it into the numerator, which means I have to indicate that as a negative exponent. Now, that particular one we learned in grade 10 and in grade 11. Whenever I have a surd, it states very clearly that surds can be written as rational exponents, meaning minus 10 x to the power of, and there's a little 1 there, so that's going to be to the power of 1 over 5. And again, people, if you go like, I never knew this, yes, you did. We taught you the definition of rational exponents in grade 10, and we reiterated, we went through it in great detail in grade 11. But I will just over here remind you that if we have any base, in this case the base could be a, to the exponent x in a surd y, then according to the rules of rational exponents, that will be a to the power of x over y. So that is rational exponents. And no, people, this is not a negative exponent. I have lots of people going, oh, but can't we write this? No, negative exponents is if you change, in this case, a number from a denominator into a numerator or from a numerator into a denominator. Surds or roots are rational exponents, in other words, fractional exponents. So please go and look at that if you are still getting confused. Now I've prepped this function. And now I'm ready to use the differentiation rules. So now I'm going to indicate dy over dx because now the rules are going to be used. So we say minus 2 times 3 is minus 6. And that's x to the power of, make this one less, subtract 1. So minus 2 minus 1 is minus 3. And then over there, we have 1 over 5 times negative 10. Again, if your fractions aren't very good, just use your calculator. So just use your calculator and go 1 over 5 times negative 10. Now that's equal to negative 2. And that's going to be x to the power of, make that 1 less again. So again, people, we're going to go 1 over 5 minus 1, which is going to be equal to minus 4 over 5. Now you can do these separately on a little piece of paper if you want to go and double check that 1 over 5 minus 1 is in fact minus 4 over 5, and that 1 over 5 times negative 10 is in fact negative 2. But again, as I said, you could just use the calculator, so you can just go and you can say, in this case, minus 10 times that exponent of 1 over 5 is then equal to the minus 2 that I've written down over there, and then you can go and you can go 1 over 5 subtract 1. So 1 over 5 minus 1, because remember the rule says always 1 less, and that's going to be minus 4 over 5, so that's why I write the minus 4 over 5. Now just a quick comment. They don't really like these negative exponents. So I always tell people, just in case, a lot of the time they give it to you as an instruction. So the instruction will specify leaving your answers with positive exponents. If it doesn't say leaving your answers with positive exponents, you can actually leave it like this. But normally, as a good habit, we just go and we change those negative exponents back to positive exponents. And again, that's simply by moving it, in this case, from the numerator down into the denominator, the sign changes. And then, in this case, it's minus 2 over x to the power 4 over 5. Now, you do not have to change these rational exponents back to surds. That is not something you need to do. But in general, just as a good habit, always change your negative exponents back into positive exponents. Now, the last little example for this video is also a past paper example, and it's specifically from the November 27 IB paper 1. So again, we want to determine dy over dx, which is the notation for the derivative. So I know I need to use the differentiation laws here. But again, I need to prep this. I need to prep the algebra first before I can go and I can find the derivative. So first things first, again, people, this is y. And the reason it's y is because I haven't yet used the differentiation rules. Now, please remember, people, pi is a constant. So pi is a constant. I'm going to write it over here. That x is currently in the denominator. I don't want it in the denominator. I need to move it to the numerator. So I will indicate that with the exponent negative 1. And then over here, the 3 is the coefficient, so I'll write it down over there. But, and you can write with that x, you can write there's a little exponent 1, and then discussing those rational exponents, this is going to be x to the power of 1 over 3. So it's x to the power of 1 over 3. Now you'll note I've prepped this particular function and it's ready for me to employ my differentiation rules. So because I'm ready to employ the differentiation rules, I can now indicate that what it follows after this equal sign is going to be the derivative of that y in terms of x. So now the moment I indicate dy over dx, I need to use the rules. So I start by saying minus 1 times pi is minus pi. X to the power of negative 2. And again, that's because I make the exponent 1 less, always 1 less. Plus, a third times 3 is 1. You can write the 1. And then x to the power of, again, make that exponent 1 less. A third minus 1. And a third minus 1 is a third minus 3 over 3, which means it's minus 2 over 3. Again, if your fractions aren't very good, please use your calculator. And just because we're trying to create these good habits, I'm not going to leave my answers with negative exponents. I'm going to quickly fix those negative exponents by moving that from the numerator into the denominator. And then again, by moving, sorry about that, let's put the 1 over there, by moving that x back into the denominator. So moving that base means the exponent is now become positive. And that is then the derivative of that particular function. Right, so in the next video, what we're going to be talking about is we're going to be talking about more past paper examples. So we're going to get stuck on this for a bit because, like I said, we cannot move forward with other examples of differentiation if you cannot use these differentiation rules. So the next video will all just be past paper examples, and I try to find some tricky ones. So you can practice all the different variations.